In this session, let us try to analyze OC test altogether in a different way. Okay, means already about OC test we discussed, and whatever the output we need to have. Okay, how to calculate shunt branch parameters we know. Now, just we have to solve problems. But machines is all about analysis. Okay, so let us analyze it means in a different way. For example, see here, if I think of what do you say, our equivalent circuit of the OC test is this. Okay, so in this we have resistance leakage like this. Okay, and here we are going to have V2 voltmeter, this is voltmeter, and we know that this is R2, this is X2, and this is R0, this is X0, this is R1, this is X1. Now here we connected one voltmeter V1 and we connected one ammeter A, which is I0, and also we connected one wattmeter. Okay, so let me drag this here. Now we connected one wattmeter here. Okay, as of now I'm not bothered much measurements, because we are not in measurements, like wattmeter should be connected first or ammeter should be connected first, something like that. I'm not bothered about it. So this is going to be wattmeter. Okay, if you want to remove the series branch, for example, if you want to move the shunt branch from here to here, what are the things we have to consider? Okay, now see here, for example, if you think of wattmeter. Okay, in wattmeter two components will be recorded. What are those? Wattmeter will record primary winding copper losses due to no load current and core loss component. Okay, so if I move the shunt branch from here to here, wattmeter is supposed to record only core loss, it will not record this. What does it mean? In my practical transformer, okay, so in my practical transformer, this is going to be the exact model. So in practical transformer, when wattmeter is connected, wattmeter will record primary winding copper losses due to no load current and also core loss component. So primary winding copper loss due to no load current plus core loss component will be recorded in wattmeter. Now if I want to shift the shunt branch from here to here, meaning that component of wattmeter reading representing primary winding copper loss due to no load current should be negligible compared to core loss component. Then only I can move the shunt branch from here to here. Let me repeat again. For example, my wattmeter is there. My wattmeter does not know that it has to record core loss only. Okay, whatever the power is being transmitted from here to here, it will record. Okay, so my wattmeter will record primary winding copper losses and also core loss. But the moment I shift from here to here, what does it mean? Meaning that my component of wattmeter reading representing primary winding copper losses should be negligible compared to core loss. Then only I can shift the shunt branch from here to here. One thing. Okay, and second thing is, if you think of voltmeter, okay, my voltmeter will record voltage across this plus voltage across this, right? My voltmeter will record voltage across the series branch plus voltage across the shunt branch will be recorded by this. So means if I shift the shunt branch from here to here, under that condition there will be no current flowing through the series branch. Okay, so there will be no current flowing through the series branch, meaning that whatever may be the component of voltmeter reading representing primary leakage impedance drop should be negligible compared to source voltage. So means compared to source voltage, the moment it is negligible, I can say that source voltage equal to this voltage. Then only I can move the shunt branch from here to here. Okay, so if I move the shunt branch from here to here, errors will happen in two meters. What are those? Wattmeter and voltmeter. Now component of wattmeter reading representing primary winding copper losses due to no load current should be negligible compared to rated core loss. One thing. And second thing is, component of voltmeter reading representing primary leakage impedance drop due to no load current should be negligible compared to source voltage. Under that conditions, I can neglect this and I can assume that this particular voltage is equal to this particular voltage, so I can shift the shunt branch from here to here. Okay, so let us analyze from this point of view. Okay, so if I analyze, okay, now see here, means normally efficiency of the transformer. Okay, so if I think of efficiency of the transformer is going to be highest among all other machines because of lack of rotational losses or because of lack of mechanical losses. Because in my rotating machines mechanically something has to rotate, means that friction and windage losses will be there. Okay, but if you think of a transformer, in transformer there are no rotating parts, it's going to be static. Okay, so the moment rotating parts are not there, mechanical losses will not be there in transformer. So because of lack of mechanical losses, I can say that transformer have highest efficiency among all machines. Okay, for example, efficiency of transformer at full load is 98% efficiency, which is possible. Okay, so at full load I can consider this as, okay, means 1% of losses will be there in the name of copper losses, 1% of losses will be there in the name of core loss. Okay, of course this particular full load efficiency I am assuming it as max efficiency. Means what is max efficiency and all we will see in the efficiency discussion. Okay, so means efficiency at full load 98% is very common thing. In that 1% losses I can consider as copper loss, 1% losses as core loss. Okay, so this is going to happen when practical transformer is operating at full load condition. Okay, now if you come back to here, see this. Okay, so when transformer is operating at full load conditions, in the sense when load connected is operating at full load, under that condition full load current will flow. Okay, under that conditions full load current will flow. So full load copper losses in secondary plus full load copper loss in primary is nothing but total copper losses. Okay, so in full load if I see in this 1% of copper loss, okay, so 0.5% for primary and 0.5% for secondary, 0.5% for secondary if practical transformer is operating at full load conditions. Now let us think of in SC test conditions, which is nothing but red. Okay, OC test conditions. In OC test conditions in secondary, how much current was flowing? Secondary is open circuited, so in secondary losses will not be there. Okay, now if you think of, if I inject full load, okay, if I inject full load current in primary, under that conditions copper losses are 0.5%. Okay, now if I inject no load current, because in OC test how much current is flowing under primary side is going to be only no load current. So if I inject only no load current, okay, how much is no load current? 2 to 6% of full load current. Okay, full load current, because in primary winding how much will be the current here in OC test condition? In OC test condition primary winding current is going to be 2 to 6% of full load current, which is nothing but no load current, because no load current is least in transformer among all other machines because of lack of air gap. Okay, so the moment if current is full load some x%, if current is half full load, my losses are going to be half square copper losses, I square R. Okay, so if full load current is happening, for example this is X, if I inject full load current X%, if I inject half full load current half square X, if I inject 1/4 full load 1/4 square X, if I inject 2 to 6% of full load conditions, full load current, under that conditions how much will be the copper loss in primary winding? Is going to be 2 to 6% square of 0.5%. Of 0.5%. Now let us think of my wattmeter reading. Okay, W0. Okay, so my W0 has to record primary winding copper losses due to no load current. Only primary winding, secondary winding current is not flowing, plus core loss component. How much will be the primary winding copper loss? Is going to be 2 to 6% square of 0.5% of rated capacity. So of rated capacity, let me leave it here. Okay, now what about my core loss component? See here. my wattmeter has to record primary winding copper losses plus core loss. The moment you supply rated voltage, rated frequency, almost rated voltage will come here. At rated voltage, rated frequency, my core loss are going to be rated. Getting my point, right? Because hysteresis losses directly proportional Bm to the power of x into f, frequency is rated, Bmax is directly proportional V by f, voltage is rated, frequency is rated, so hysteresis losses are going to be rated. Now, if you think of eddy current loss, rated voltage you are supplying here, so eddy current loss are going to be rated. Now, how much are the eddy current loss here, total core loss here are 1% when the transformer is operating at rated conditions. So, as of now, it is operating at rated voltage, rated frequency, so this is going to be 1% of rated. So, how much is the wattmeter reading? 1% of rated capacity plus 2 to 6% square of 0.5% square of rated capacity. So compared to this, definitely this can be neglected. For example, let me take maybe my transformer rated capacity is 10 kVA. My transformer rated capacity is 10 kVA. Under that conditions, how much is 1%? Is going to be 1 by 100 of 10,000. Of 10,000 is going to be 100 watt. Okay, so 1% of rated capacity is going to be 100 watt. Okay, let me think of this as 5%. So 5% square. So this is going to be 5 by 100 multiplied by 5 by 100 multiplied by 0.5 by 100. 0.5 by 100 multiplied by rated capacity is 10,000. 10,000 is going to be how much? Is going to be 1, 2, 3, 4, 5, 6. 4 will go. So 5, 6. 0.5 into 0.5 into 0.5. 0.125. Okay. So 25. Yes. 125. Okay. So this is going to be 0.125. So my wattmeter reading is going to be 100.125 watt. So can I approximate it to 100 watt? Yes. Okay, so it's a small thing. Don't get tense. Like we need not get scared. Just we are analyzing. How we analyze? Our thing is wattmeter reading. Wattmeter reading in the sense losses. So for example, practical transformer is there. For example, practical transformer is operating at full load conditions. Full load conditions in the sense rated voltage will be there and rated currents also will flow. Under that conditions, it is having 98% efficiency. Means that 2% losses will be there roughly. Okay, in that 1% losses, let me allocate to core loss, 1% of losses, copper loss. Okay, so in practical transformer, when my copper winding of secondary is operating at rated conditions and my primary is also operating at rated conditions, total copper loss is going to be 1%. Now, means in secondary plus primary copper losses, secondary copper loss plus primary copper loss are going to be 1%. Means that secondary 0.5%, primary 0.5%. In secondary, now this is the practical case. Now, if you come to OC test conditions, how much is the secondary copper loss? 0. So, in primary, if you inject full load current, it is 0.5%. If you inject half full load current, half square 0.5%. If you inject 1/4 full load current, 1/4 square 0.5%. What is the no load current now? 2 to 6% of full load current. So, if you inject full load current in primary winding, copper loss are going to 0.5%. If you inject 2 to 6% of full load current, copper loss in primary winding will be 2 to 6% square of 0.5%. 0.5%. So, means about copper losses, we got the clarity. Now, if you think of core loss, in a practical transformer, core loss are 1%. Now, in OC test conditions also, you are supplying rated voltage. You are supplying rated frequency. So obviously we can say that whatever the core loss are happening in OC test conditions are exactly equal to practical transformer core loss component, because practical transformer rated voltage, rated frequency, here also rated voltage, rated frequency. So core loss I have taken fully. So my wattmeter has to record core loss component and also copper loss component. Now as per the percentages, if I assume 10 kVA capacity of the machine, under that conditions 100 watt is going to be 1% core loss and 0.125 watt is going to be copper loss. 100.125 can be assumed into 100 watt. Means that extra 0.125 can be negligible. So what does it mean? What is my conclusion here? In this wattmeter, wattmeter reading, two components will be there. One component is going to be primary winding copper losses, secondary component is going to be primary winding core loss. So primary winding copper loss can be neglected because that magnitude is negligible compared to rated core loss. So I can move the shunt branch from here to here. Okay, now let us think about the voltmeter. Now let me what do you say, erase this. Okay, now if you think of voltmeter, okay, normally we know that my leakage reactance or leakage flux or leakage reactance or leakage impedance is going to be very less in transformer. Why it is least in transformer? Because of lack of air gap. Leakage is going to be least, leakage flux is going to be least, leakage reactance is going to be least, leakage impedance is going to be least, voltage drop across leakage impedance is going to be least. Okay, now for example, I have 250 volts by 2500 volts. Example, let me consider. Okay, so let me consider blue, as we have taken previously also blue, 250 volts by 2500 volts transformer. Now, if you try to draw equivalent circuit, resistance, reactance, shunt branch, okay, here this is resistance, reactance, okay, so this is R2, this is X2, this is R1, this is X1, this is V1, this is V2, means this is E2, this is E1, and this is going to be I2, and this is going to be I1. Okay, now let us see. For example, means let us assume that for time being this particular thing is not there. Okay, so for time being this is not there. Okay, now what will happen with respect to voltage? V1 minus drop is going to be E1, E2 minus drop is going to be V2. Okay, so actually if I reflect everything to the secondary side, I can say that R1 plus X1 dash. So if I try to model this, some voltage source, this is the reactance, so this is V2. Okay, of course ideally it is not E2, but we can consider it as E2 because most of the books are following. Okay, let us keep it as E2. Okay, now R2 plus R1 dash RE2. Okay, RE2 I'm keeping it as a R2 plus R1 dash. You know how to transform from this side to this side the impedance, N2 by N1 square. Okay, anyway, we know that LV to HV how to transform, HV to LV how to transform. This is more than sufficient. Now after that, XE2, this is XE2 X2 plus X1 dash means that this is going to be ZE2. Okay, long back we have taken one example, that is, for example, this rated voltage is 100 volts and this is 1 ohm and rated current for this is 10 amperes. At no load, how much voltage will come? 100 volts. Okay, now for example, if I fully loaded the load, okay, so if I extract full load current, how much is the full load current? 10 amperes. So if I take 10 amperes, it is going to be 10 into 1, 10 volts, and this is going to be dropped to 90 volts. Now at that time I told you that the moment, for example, this 1 ohm resistance is small. Okay, so if this impedance is small, voltage drop across leakage impedance is going to be small. Okay, so the moment voltage drop across leakage impedance is small, terminal voltage variations is going to be small. Okay, for example, this is 0.5 ohm only. Under 0.5 ohm condition, rated current of 10 amperes, how much will be the voltage? 5 volt. So 100 minus 5 is going to be 95. Okay, so the moment leakage impedance or kind of internal impedance of the generator is small, automatically voltage drop across total impedance is going to be small. Under that conditions, terminal voltage variations is going to be least in transformer, because in transformer XE2 is going to be least. because of lack of air gap. And Re2 you cannot do anything because in all the machines resistance is going to be same in per unit. So the moment Xe2 is least, Zu2 is going to be least. If Zu2 is least, automatically voltage drop across Zu2 is least. Under that conditions, terminal voltage variations are going to be least. Okay, that terminal voltage variations for a practical transformer, maximum voltage regulation, we say that will vary normally from 6 to 12%. Okay, so under full load conditions, okay, if I take full load current, under that conditions terminal voltage vary 6 to 12%. That is the maximum voltage variation in transformer. For example, come back to here. For example, if I consider full load current here, under that conditions my voltage variation is going to be 6 to 12%. Okay, in the next SC test I will explain you how R2 equal to R1 dash, or how R1 equal to R2 dash, or Z1 equal to Z2 dash, or Z2 equal to Z1 dash. I'll explain in the SC test immediately after this. Anyway, if voltage variation here is 6 to 12%, I can say that voltage variation is 3 to 6% here, voltage variation is 3 to 6% here. Okay, in percentages. So because why this particular Xe2 is going to be least in transformer? Why? Because of lack of air gap. Okay, so again relax. Okay, even without knowing all these things also we can solve the problem of transformer. Okay, because already OC test how to calculate shunt branch parameters and all we know. Okay, but still we need altogether different analysis. Why? Because if we analyze more and more in machines, automatically our hands-on experience will be more, such that our grip over the subject will be more. We will be able to think in multiple ways in order to crack the exam. Okay, because machines is not like mathematics, machines is not like networks. Even though I'm taking networks, it is not networks. Okay, boundaries will be there in machines. Anyway, like again, let me start. The moment this is least, voltage drop is going to be least, terminal voltage variations will be least. That variation is 6 to 12%. So 6 to 12% here means that 3 to 6% here, 3 to 6% here. In the next session of SC test, I am going to tell you like Z1 equal to Z2 dash or Z2 equal to Z1 dash in SC test immediately after this. Okay, now forget about it. Now if you see, if you inject full load current, how much is the voltage drop here? 3 to 6%. How much is the voltage drop here? 3 to 6% if I take full load current. Now let us think of OC test conditions. In OC test conditions, how much is the current in secondary? 0. I2 is going to be 0. So this is going to be 0. Okay, now if you think of here, if you take full load current, this is some X% of voltage drop. If you inject half of full load current, it's going to be half of X. If you take 1/4 of the full load current, it's going to be 1/4 of X. Because if current is reduced by, for example, K times, automatically voltage drop also will be reduced by K times because it is linear. Okay, now for example, in OC test conditions, secondary current will not be there, and this particular current is not full load current, but this is 2 to 6% of full load current. Okay, now if you take full load current, voltage drop is 3 to 6%. Now under OC test conditions, in the sense blue means full load current some X%, 2 to 6% of full load current, 2 to 6% of X%. So this is going to be 2 to 6% of 3 to 6% of rated voltage. Okay, so means what is the voltage drop here across the series branch in no load conditions, in OC test conditions, is going to be 2 to 6% of 3 to 6% of rated. So for example, let me erase this. My rated voltage is, for example, 250 volts. Okay, now if I connect voltmeter here, V rated, how much will be V rated? For example, this side V rated will show you 250 volts. Now in this 250 volts, two components will be there. Voltage drop across this will be there, and voltage drop across shunt branch will be there. Okay, voltage drop across this plus voltage drop across this equal to this. So in this 250, I have two parameters. What are those? 2 to 6% of 3 to 6% of rated voltage, and 250 minus this is going to be this. Okay, so how much is 2 to 6%? For example, common 2 to 6% common, let us take 5%. 3 to 6%, let us take 5%. So this is going to be 2 to 6% of 3 to 6% of rated voltage. Rated voltage is going to be 0.625 volts. Okay, 520, yes, 4 zeros, yes, 0.625 volts. So supply voltage is 250 and voltage drop across the series branch because of no load current is 0.625. So with respect to 250, I can neglect this and I can assume that this E1 as 250 volts. Okay, now I can say that if I have voltmeter here, okay, see here, if I have voltmeter here, which is supplied with rated voltage, definitely voltage drop will be there across a series branch, but that particular voltage drop in series branch because of no load current, is negligible compared to rated supply voltage. So directly I can say the supply voltage is nothing but back EMF here, means voltage across the shunt branch here. Now I can move the shunt branch from here to here. Okay, so means if I just have a small recap. Okay, so we started like this. My wattmeter error will be there, in voltmeter error will be there in consideration. Okay, because my wattmeter will measure copper losses here and core losses here, but later we found that component of wattmeter reading representing primary winding copper loss due to no load current is negligible compared to rated core loss, so neglect this. Now second thing is my voltmeter will record voltage across this plus voltage across this. Okay, so voltage across this plus voltage across this, I'm sorry, okay, now my voltmeter will record voltage across this plus voltage across this. Now we came to know that under no load conditions, voltage drop across series branch parameters due to no load current is quite negligible compared to supply voltage. So by neglecting this, I can consider the same voltage is appearing here, so I can move the shunt branch from here to here. Okay, so conclusion is very simple. Once we move the shunt branch from here to here, we know how to calculate. Already we discussed in our previous lecture. Okay, now we know how to calculate, but interview question here is, okay, means I said that at any cost this particular test should be conducted at rated voltage and at rated frequency only. Okay, at rated voltage and at rated frequency only. Is it possible to conduct this particular OC test at other than rated voltage and rated frequency? No. And yes also. Let us see. For example, let me consider three things. Okay, so let me consider three things. Let me erase this. If I supply rated voltage, rated frequency, what will happen? Okay, if I supply means other than rated voltage, other than rated frequency, by not maintaining V/F ratio constant, what will happen? If you supply other than rated voltage, other than rated frequency, by maintaining V/F ratio constant, what will happen? So three things we are going to discuss. Maybe the first case. So let us think of first case, that is black. Black is at rated voltage and at rated frequency. Okay, now let me think of the second case. The second case is red. So in the second case, let me consider at V rated by 2 F rated. V/F ratio is not maintained constant. Now let me consider case 3. Case 3, this is going to be at V rated by 2 and F rated by 2. F rated by 2 means that I am trying to conduct my test at other than rated voltage by maintaining V/F ratio constant, because the moment you maintain V/F ratio constant, automatically Bmax is going to be constant. Keep an eye there. Okay. Now let us think of in the first case. In the first case, if I maintain rated voltage, rated frequency, let me draw BH. Okay, so this is going to be B rated. This is going to be B rated with B rated. Okay, so with B rated, let me take a bit bigger one. This is better. Okay, so this is going to be B rated. This is going to be B rated. Now, if you think of hysteresis loss, because what my wattmeter will represent? My wattmeter W0 will represent hysteresis loss and eddy current loss. Okay, hysteresis loss directly proportional to B max to the power of X and F, directly proportional to voltage square. Okay, now what is B max? B max directly proportional to V by F. Okay, so the moment it is rated voltage, rated frequency, rated voltage, rated frequency, rated flux density, rated frequency, rated hysteresis loss, so it is going to be rated. Now, the moment you supply rated voltage, eddy current loss are rated. So, I can say that this is rated means that my core loss are going to be rated, means that from here, means from W0, if I calculate R0, I can use this R0 in the practical analysis of the transformer. Okay, because rated, my wattmeter reading will give you rated. Under that conditions, from wattmeter reading means because my wattmeter reading has to be absorbed by R0 only, no? Okay, R0 rated you are going to get. Now let us think of the second case. Okay, so in second case, what is my B max? Voltage is reduced by half and frequency is rated. So V by F ratio, B max is going to be half. So this is going to be, this is B rated by 2. This is B rated by 2. Okay, so if this is B rated by 2, let us think of this area. My red is going to be hysteresis area is going to be this. Okay, now let us think of again here W0, because if you conduct your test at rated voltage by 2 and frequency rated also, you are going to get some W0, no? Some W0. Now this particular W0 will have hysteresis loss, will have eddy current loss. Okay, now if you think of only voltage, because my eddy current loss are independent of frequency, so voltage is reduced by half. So eddy current loss are directly proportional to voltage square. So voltage is reduced to half, means that eddy current losses will be rated by 4. Eddy current losses rated by 4, because that is of this by 4. Okay, now what about hysteresis loss? Because point here is very simple. What is that? Ultimately, my practical transformer will operate at rated voltage, rated frequency. For example, if this is my practical transformer which is designed for 11 kV 50 Hz, normally you will operate this at 11 kV 50 Hz only. You don't operate this particular transformer at 5 kV. Right? Because if you operate it at 5 kV, what is my kVA capacity? Voltage is reduced, so kVA capacity will be reduced. So the machine capacity will be derated. Machine capacity will be reduced. Then you will not be called as an engineer. Getting my point, right? So if you see here, hysteresis loss, because ultimately my transformer you are supposed to use at rated voltage, rated frequency. At rated voltage, rated frequency of practical utilization, in my testing conditions also you are supposed to get in testing the same value of practical. Otherwise your test is going to go in vain. It's of useless. Okay, so if you think of hysteresis, for example, from black area of BH. Okay, from black area of BH, is it possible to get red area? No, because they are not mathematically defined. For example, if you think of a circle, big circle, half of the radius circle, area will be 1/4, something like that, we can, because mathematical interrelationship will be there between two areas of circle, two areas of triangle, two areas of mathematically defined functions, but they are not mathematically defined. So from this black area, you cannot find red area. Means that from this here you cannot find, from this you cannot find hysteresis rated at all. There is no mathematical interrelation. Means that from W0 it cannot be W0 rated. Under that conditions, whatever you are going to get cannot be R0R. Okay, so my OC test cannot be conducted at other than rated voltage by not maintaining V by F ratio constant. Now, let us think of the third case. Blue. Okay, now if you think of the third case, V rated by 2. Oh, sorry. Okay, so V rated by 2, F rated by 2. So V by F ratio is maintained. So B max is going to be same. So if you see, okay, blue line also, B rated will be here only. Now, can I conduct my test there? No. See. Of course, in the exam we say that it cannot be conducted, but in interview we will fight that. It can be conducted that way. Okay. Now, for example, this is V rated by F rated by 2. Now, let us think of which will have component of hysteresis loss, have component of eddy current loss. Eddy current loss will be decided by voltage only. So, voltage is half of the rated voltage is supplied. So, this is going to be eddy current rated by 4. If you can find eddy current losses separately, by 4 will give you, 4 into eddy current loss will give you rated eddy current loss. From that rated eddy current loss, we can find R0, through which you can find R0R. Now, if you think of hysteresis, okay, so what is hysteresis loss? Directly proportional to B max to the power of X into F. B max is constant, directly proportional to F. Now, frequency is half. So, hysteresis loss is rated by 2. So, means what is W0 now? W0 equal to hysteresis rated by 2 plus eddy current rated by 4. Okay, but in order to find R0, I need hysteresis rated plus eddy current rated. From only one equation, how can you find W0 R? Core loss rated, how can you find? Without calculating W0 R, how to find R0 R? Not possible. So, means even after maintaining V by F ratio constant, OC test should not be conducted at other than rated voltage. Okay, so other than rated voltage, even after maintaining V by F ratio constant also, OC test should not be conducted. That is like kind of exam. Most preferably, they may not cross beyond it. Okay, but in interview, for example, means I felt that, okay, I'm an egoist. Yes, okay, I don't want to conduct at rated voltage, rated frequency at all. Okay, so without that, is it possible? Yes, it is possible. For example, rated voltage, rated frequency by 2 if I conduct one test. Now let me conduct another test at V rated by 3, F rated by 3. Now let me calculate this as 1. Now this as 2. Okay, 2 is going to give you hysteresis loss equal to hysteresis loss rated by 3, eddy current loss equal to eddy current losses rated by 9. Okay, so he makes total core loss 2 equal to hysteresis loss rated by 3 plus eddy current loss rated by 9. Okay, so this is first equation, this is second equation. From first and second equations, because point is very simple, means if you don't want to conduct your OC test at rated voltage at all, there is a possibility. But in that case, after maintaining V by F ratio constant at two operating points, you are supposed to conduct OC test. Okay, now if you see here, means we solved some problems, right? Maybe after maintaining V by F ratio constant, in case 1 maybe at 50 Hz 400 volts some core loss, at 25 Hz 200 volts some core loss, maybe at other than that frequency, means how much will be the core loss, or how much will be the hysteresis loss and eddy current loss, or how much will be the ratio of hysteresis losses to eddy current losses. Already we solved some problems in core loss. So in the same way we can solve. In the same way we can solve. So conclusion is very simple. Normally means we have to conduct our OC test at rated voltage, rated frequency only. We should not conduct OC test at other than rated voltage by not maintaining VBF ratio constant. We should not. Now OC test can be conducted at other than rated voltage, but we have to maintain V/F ratio constant at 2 operating points. OC test should be conducted. In that way we can find the remaining things. Now let's start SC test.